Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We're at lecture 4.6. We're going to be covering a work-efficient parallel scan kernel. The objective of this lecture is to help you to learn to write a work-efficient scan kernel. We're going to introduce a two-phase balanced tree traversal approach to minimize the amount of work. And in the process, we're going to aggressively reuse the computation results to avoid doing more work. And also, we're going to be using a fairly sophisticated thread index to data index mapping to reduce the control divergence. And this mapping is going to be more sophisticated and complex than the approach that we introduced in the reduction tree lecture. And I'm going to go over why and how we can do this kind of trade-off. To improve efficiency, we're going to use the concept of balanced trees. And for those of you who have taken data structure, you know a balanced binary tree is a tree where every node has two descendants, and then the tree is always balanced. You always have the same number of descendants on each side of the tree. So we're going to form a balanced binary tree on the input data, and then we will use the threads to sweep through that tree from the leaves to the root, and then from the root back to the leaves. This is not an actual data structure. The tree is not the kind of data structure that you typically have in the data structure courses where you have the links from a parent to its children, but rather it's a conceptual way of thinking about at each iteration or each step which thread should be taking action and how the action should be done. So for scan, we're going to traverse down from the leaves to root, building a partial sum at the intermediate internal nodes in the tree. And essentially what we're doing is we're at each step, whenever we compute a partial sum, we will be updating one of the data elements in the shared memory. And we'll be doing this as an in-place computation algorithm, meaning that the original contents of the shared memory array are the original elements, but we will be updating these elements towards the final outcome. And many of these elements will be holding partial sums during the computation. So at the end of the reduction phase, the root will hold the sum of all the leaves. And then after the first phase, we're going to take that second phase where we're going to traverse back up the tree, building the output from these partial sums as we go. So here is a quick illustration of the reduction phase of parallel scan. So we start by having all the elements in a shared memory array, and then we perform multiple iterations. For 8 elements, we're going to perform 3 iterations, just like the reduction tree lecture. And in the first iteration, we're going to form pairwise 2-element sums of neighbors. And then in the next iteration, we're going to form 4-element sums from these 2-element sums. And again, we're going to be using neighbors. And finally, we're going to form 8-element sums from 2 4-element sums. And as you can see, we're going to be doing in-place calculation, meaning that some of the element positions will be updated from the original value into these partial sums. And some of the sums are going to give us final value. For example, the x3 position has the final answer because it contains the sum from x0 through x3. So this position is pretty much all set as the final answer. Same with x7. And x7 now contains the sum of x0 through x7. So that gives us the exact answer that we want for that position. And we also have some locations where these values are not the final answer. For example, x5 position has only the sum of x4 and x5. We're still missing x0 through x3. Obviously, the even elements are pretty much all far away from final answer because they still contain the original element values. So here is the kernel code for the reduction phase. And we assume that we have a compile time constant called block size, which is half the number of elements in each section. And so block size really gives us the number of threads that we have in each thread block. And each thread is going to be responsible for loading two elements. So it's really half the size, the number of elements in that section. So we will allocate a shared memory that of size of 2 times block size that will hold all the elements in the shared memory array, XY. And then we will go into this iteration. So this is the iteration where we traverse the reduction tree from leaf to root. So we will start with stride 1 because that will give us that pairwise addition in the first iteration. And then we will double the stride by 2 after every iteration. We will iterate until the stride is equal to the number of the threads in the thread block, or half the size of the number of data elements in the section. So here is the part that is different between this particular kernel and the one that we introduced in the reduction kernel. In the reduction lecture, we used an approach where we added the element of a particular position to an element that is far away from it. So that's how we preserved the property of consecutive threads. All the active threads are consecutive so that we can minimize the control divergence. However, here, because the requirement of these partial sums, we really needed to do the neighboring the pairwise sum for neighboring elements and so on. So we don't have the option to switch to the addition to 2 elements that are far away. So this particular approach allows us to still have a consecutive group of threads that are active, but we map all those thread indices into the spread out data indices that we need during each iteration of the computation. So here is the formula. It looks complicated, but it's actually quite simple once you dissect it. So first we add 1 to the thread index. So for the thread index, we have from 0 through block size -1. But after we add 1 to the thread index, we have 1 through block size. So this is really just to give us all the non-zero consecutive integer values from 1 to block n minus 1, from 1 to block size. And then we will multiply this value by stride and then multiply by 2. And this is really just to give us a perfect power of 2 that is 1 power above the stride. Remember, stride is also going to be a perfect power of 2. So when stride is 1, we're going to be multiplying by 2. And stride is 2, we're going to multiply by 4. When stride is 4, we're going to multiply by 8. So in the first iteration, because we multiply by 2, stride is 1, we're multiplying the thread index plus 1 by 2, we will be producing all even numbers. And then we subtract 1, so we ended up generating all odd numbers from 1 to block size. So this gives us 2 times block size, not block size. So this gives us all the odd positions that we need to map the threads to in order to calculate the first iteration results. So thread 0 now will be in charge of x1, thread 1 will be in charge of x3, thread 2 will be in charge of x5, thread 3 will be in charge of x7. And in the next iteration, because we're going to be multiplying those the indices by 4 now, so then we'll subtract by 1. So thread 0 will be mapped to 4 minus 3, 4 minus 1, which is 3, and thread 1 will be mapped to 8 minus 1, which is 7. So we're going to just have those two threads active because we do a if test in the code where the index has to be less than the number of data elements that we have in the in the section. So we perform this addition, and then we will do a sync thread. At this point, you should ask me, how come we don't see two sync threads as we did in the work inefficient kernel? The reason why we don't need to have two sync threads has to do with the particular structure of this computation. If we look at all the positions, elements that will be changed in the after each iteration, let's say iteration 1, the elements that will be changed are x1, x3, x5, x7, all the odd elements. If you look at these elements, none of these elements are used by any other threads other than the thread that is directly computing its result. So unlike the work inefficient kernel, there's no danger for a thread to change the contents of its position too early that another thread may incorrectly get the outcome of the thread computation rather than the original value. So this is the reason why we don't need to have another sync thread to guarantee that all the threads have secured their input value. Now we can move on to the post-reduction reverse phase. And after we have all these partial results in the in these element positions, we will start to sweep back from root back to the leaves. And the point of the computation is to, as quickly as possible, assemble the final result from these partial sums. And if we look through all the partial sums, the one at position x5 is the one that is the farthest away from the output value because it is missing all the values of the first half of this array, and then it's so we really need to quickly ship the effects of those value or accumulate those effects of the value into this position. So this is why we take the middle position here and we add the partial sum of x0 through x3 into that position. So this quickly brings us brings that position up to the final outcome. So this is a very strategic move that brings the data into a position that is going to be, it will update the output very quickly, and also this outcome is going to be used by others, such as x6, to quickly bring them to the final result. So this allows us to do just one more step and bring everyone to the final value. So x2 can be brought to the final value by just adding the sum of x0, x1 into it. And then x4 can be brought to the final value by just adding the sum of x0 and x3 into it. And x6 can be finished by just adding the sum of x0 through x5, which we produced in the previous iteration, into it. If we put it all together, this is a 16-element case where we have the reduction phase, and then we have the post-reduction reverse phase. And we show that it's the same thing. And after the reduction phase, we're going to need to bring the central value quickly into the 3/4 position, and then we would need to bring the next, essentially the next level of values into the 2 positions to the right, and then we need to just we are in the position where we can just add all these essentially all the remaining locations, all the remaining essentially even positions by the partial sum that is to their left, because these partial sums are essentially already have all the accumulated values from all the preceding locations. However, if you look at these positions, it's actually pretty hard to map the thread indices into those positions. It's kind of awkward. So what we're going to do is we're actually going to have the threads to be mapped into the left. For each pair of the addition we need to do, we're going to actually map the threads into the left position rather than the right position. And then after the addition of those two values, we're going to write into that mapped position plus stride value. So this allows us to use a simpler thread thread index to data index mapping and achieve exactly the same result. For example, in this in the 16 element situation, we needed to add element at location 7 to the element at location 11. So instead of mapping the thread, the one active thread to location 11 and fetch from location 7, add to the 11 or write into 11, we're going to map the active thread to location 7. And we're going to add the value of 7 and 11, and then we're going to write into 11 rather than 7. So this allows us to use exactly the same thread to data index mapping as the reduction phase, but by changing the output, the way we fetch the input and write into the output slightly, we can use just as simple a mapping scheme, but accomplish exactly the same outcome. So this brings us to the post-reduction reverse phase kernel code. We're going to take those iterations, and we're going to start with stride value to be 1/4 of the data section size, which is half of the thread block size. So we start with that half thread block size stride, and we will divide the stride value by 2 in each iteration, after each iteration. And we will do a sync thread to make sure that the previous iterations have finished their job. And especially this sync thread is going to make sure that the previous reduction step has already also done its job. And then we do exactly the same index calculation as we did in the reduction phase. So this goes back to the to the 7 versus 11 explanation I just made. And then we will test whether the mapped position, which is index plus stride, has exceeded the valid data range. If it's within the valid data range, it's going to take its mapped location, which is index, and then the right-hand side value, which is index plus stride, add them together and push the value into index plus stride location. So this is writing into that the location stride away from your mapped location. So this adjustment of the output expression allows us to use that simpler thread to data index mapping, but still accomplish the same effect. After we finish all the iterations, we're going to come out and write a result from the shared memory into the global memory. So just as a quick example here, in the first iteration for 16 element section, the thread index, only one thread will be active according to our previous picture. So if we look at thread IDX, the 0 thread, its stride value in the first iteration is going to be half of the block size, which is 4. And then thread IDX.x plus 1 is going to be 1 for thread 0. So 1 times 4 times 2 is going to give us 8. And 8 minus 1 is 7. So thread 0 is going to be mapped to position 7, which is exactly where we want. It's in the middle of the data structure. And the stride size is going to be 4, so it's going to be adding position 7 and position 11, which is 7 plus 4 together. And it's going to write into location 11 as we wanted to do. And thread 1 is going to produce a sum of 2 in the index calculation. So we'll have 2 times stride equal to 4, which is 8. And then we times another 2, that's 16. So well, when we have 16 minus 1, it's already bigger. When we do the test, it's going to be exceed it's going to be right at it's 2 times, let me see, it's thread IDX is 1, so it's 2 times stride, which is 4, which is 8, and then another 2 is 16. And 16 minus 1 is going to be exactly exactly 15. But then when we add stride value, which is 4, into the index, it's going to exceed the 16. It's actually going to be 4 plus 15, which is 19. So that thread 1 or any thread that is above it will be disabled by the if statement. So this guarantees in that first iteration only one of the threads, thread 0, is going to be active, doing exactly what we expected to do. So this brings us to the end of the lecture. And for those of you who would like to learn more about work efficient kernel scan kernel design, I'd like to encourage you to read sections 9.4 and 9.5 of the textbook. Thank you.